Remember that we said that one-dimensional systems are characterized by waves that travel in only one direction. For the ideal string, the displacement is in one direction, up and down, as the string oscillates. But there is another way to look at the plucked string. If we stretch a long rope or string under tension and whack it at one end, we might observe that the pulse that we introduce travels along the rope, just as sound propagates through the air. When that pulse reaches the boundary at the other end, it is reflected with an inversion and travels back to our end, reflecting with inversion again off of my thumb, and so on until the losses due to friction and other dampings cause the wave to die away. And of course, it does that exponentially. This observation of one-dimensional traveling waves traveling up and down the string gives us a super physical and really efficient way to simulate the plucked string. In fact, another French guy named D'Alembert posed this solution to the wave equation in one dimension. D'Alembert's solution decomposes it rather than into sine waves, as Fourier did, into left and right going wave components along the string. This equation states that the string behaves as the sum of two waves, one traveling in each direction along the string. We aren't able to see the individual left and right going waves when we play our guitar or ukulele, just like we can't see the individual Fourier harmonic sine waves that make up the modal solution. But D'Alembert's math doesn't lie, and now we have another way to simulate the plucked string. Let's look at this in a discrete simulation animation, where we can easily see that a pulse excitation splits in half into left and right going traveling components. These reflect with inversion at the ends and join back together in the center as a negative pulse, and so on. We can also pluck our D'Alembert simulated string with an arbitrary shape, like a triangle, like plucking it in the center, or a pluck towards one end. If we run the simulation, we see that breaks up into left and right going components, the sum of which at the top is always the string shape, reflection with inversion at the far end, and then propagates back to the original pluck shape, minus perhaps some losses due to friction and other things going on in the string. But of course, we don't want to solve the pluck-struck string in this exhaustive way either, for every point on the string 44,000 or more times per second. And of course, there's a much cheaper way. In fact, the cheapest way known to solve the string equation. Back in the early 1980s, some people worked out efficient ways to model D'Alembert's traveling wave solution to the string equation so that it could run in real time, or at least really fast, on digital computers of the day. Rather than me telling you about that, I'm going to bring back Julia Smith to tell us more about those models and how they came to be.
The Karplus-Strong algorithm is a wavetable synthesis algorithm where the wavetable is initialized with random numbers or some other set of numbers and some kind of wavetable modification scheme that operates on those numbers. One sample at a time is used. So Karplus and Strong were working on an 8-bit microcomputer, and the wavetable synthesis sounded pretty static, and they came up with the idea of dynamically modifying the wavetable as was being played. So the one that was very popular was the 2-point average modification. Now you can also draw that algorithm in a signal processing diagram, and in that case it looks like a delay line with a feedback loop around it, so like a comb filter. And the modification step is, if it's a 2-point average, then it's a little low-pass filter in the feedback loop. So a feedback comb filter with a low pass in the feedback loop is essentially what the architecture was for the guitar-like sounds. The original carpetless Strong algorithm, said to be invented by Alex Strong in 1978. I referred to the 1983 paper in the Computer Music Journal in preparation for this interview. It's really the one that most people use and know about, and it uses the simple 2-point average for filtering in the feedback loop. In fixed-point arithmetic, that requires no multiplies. It's really just a sum and a right shift by 1 bit. So an 8-bit microcomputer could do this really fast. So a 0 multiply guitar algorithm. So this version sounded so much like a guitar, they actually named it the Digitar algorithm. And they got a patent. They licensed it to Mattel, as I recall. And so it was a real breakthrough in guitar-like timbres. But they also had other variations. Another variant, for example, is the drum synthesis variation, where you randomly negate the output of the 2-point average in the feedback loop. And there's a probability controlled called the blend factor. So you can decide how much toggling of the sign that you want, and it makes a kind of snare drum kind of sound. And there are other variations, and you can find them in the 1983 paper in the Computer Music Journal, which is where that was all announced. It creates a lot of stochastic high-frequency energy. So that's what makes it sound drum-like. I would say snare-like. There was one called bottle mode, and I don't remember exactly how to do it. I can't specify the algorithm, but bottle mode was another one that was pretty nice.